Today's experiment is about Experiment 10, Determination of Optimum Moisture Content using Standard Proctor Tests performed by Group 4 of CE14E2, which consists of Galarrita, Guiling, Gulay, and Honculada.
We based our laboratory procedures from ASTM-D 698 or AASHTO 91. The standard proctor test is performed to know the compaction characteristics of different types of soil with respect to changes in moisture content. It is done in order to study and understand the soil's compaction characteristics, reaching optimal moisture content where the soil becomes dense and subsequently gains its maximum dry density. The materials and lab equipment to be used are compaction rammer, mold assembly, brush, mason hammer, trowel, graduated cylinder, number 4 sieve, large metal pan, and coarse-grained soil. For the procedures, put the prepared soil in the large metal pan. Make sure that the soil to be used is dry enough. Use a mason hammer to break the soil into finer parts so that it can pass through the number 4 sieve. After breaking, put it on the number 4 sieve using trowel. Shake the sieve for about 30 seconds. Remove the unwanted large particles. Put the soil that passed through the number 4 sieve in another large metal pan. Repeat the processes mentioned until the mass of the soil is about 6 to 8 pounds. Measure the mass of the mold assembly, graduated cylinder, and the volume of mold. In our case, the mold assembly is 7.895 kilograms. The graduated cylinder is 680 grams, and the volume of mold is 2032.22 cubic centimeters.
Put the soil in the mold assembly and measure its mass. The mass of the soil is 3.55 kilograms. Prepare for the volume of water required to add to the soil based on the moisture content. We started with a 4% moisture content, so we poured 142 grams of water into the soil. Mix it using the trowel. After mixing, put it in the mold and use the compaction rammer, in which it must be dropped from the height of 12 inches and perform 25 blows. After compaction, we removed the excess soil in the mold, cleaned its base, and we measured its current mass. Our next moisture content was 11%, so we poured 248.5 grams of water. We mixed, put it in a mold, and compacted it, and measured its mass again. We poured 106.5 grams of water for the 14% and 17% moisture content. Mixed and compacted it, then measured its mass. Our next moisture content was 22%, so we poured 177.5 grams of water. Since the mass is still increasing, we jumped to 30% moisture content that requires 284 grams of water. The mass finally decreased. Solve for the density, which is mass of the mold with soil over the volume of mold, of each moisture content, and plot it in a compaction curve graph.
As what we can see in the table, we started with a 4% moisture content with a mass of 9.025 kilograms and a corresponding density of 4.44 times 10 to the power of negative 3. After that, we increased the moisture content to 11%, getting a mass of 9.220 kilograms and a density of 4.54 times 10 to the power of negative 3. Next is that we increased to 14% of moisture content, having a soil and mold mass of 9.480 kilograms and a density of 4.66 times 10 to the power of negative 3. As we observe that the density is still increasing, we increased the moisture content to 22% directly. With this, we were able to reach the optimum point of its mass of soil, which is 10.005 kilograms and a density of 4.92 times 10 to the power of negative 3. Subsequently, we increased the moisture content to 30% right away so that we can observe the possible changes of its mass and density. After adding the 30% moisture content, the mass of soil and mold started to decrease, which is now 9.845 kilograms already, as well as the density, which is now 4.84 times 10 to the power of negative 3. The x-axis of the compaction curve is the moisture content, while the y-axis is the density. Based from the graph, it can be seen that from 4% to 22% moisture content, it was still increasing. Meanwhile, it decreased from 22% to 30%. The optimum moisture content is 22%. Our graph resembles the expected outcome, which is bell-shaped curve.
Conclusion: the standard Proctor test performed by our group was able to achieve the desired parabolic graph. We were able to accurately test out samples of 3 to 8% increments of water content. With that, we were able to plot out its maximum density around the 20 to 25% water content mark. The soil was at its heaviest and dense at those points, and it yielded the maximum weight. After the 30% mark, the soil starts to become sludgy and rubbery, making the soil lose water because it cannot hold water anymore. The results are convincing because it showed the rising and falling of the soil weight. The group decided to stop at the 30% mark after it showed that its weight was less compared to the previous point, indicating that greater than 30% X was the start of the downward trend.